Okay, let's try that again. Okay, so for real this time, welcome everybody to another edition of the Gemini North Talk series. We are coming to you today from the old Caltech Submillimeter Observatory building, which is now the TMT building. They were gracious enough to host us after the unfortunate incident that happened 1 week ago today. Today we have Dr. Olga Cucciati joining us from Bologna. Olga and I have been longtime collaborators working on galaxy evolution as a function of environment. Olga got her PhD in University of Milano way back when, and then went on to a postdoc at ENAF in Milano, and then in Marseille, where she worked under Laurent Stress to do something as simple as measure all the stars that are forming in the universe at intermediate and high redshifts. And then she went on to Trieste and eventually to Bologna, where she's been for ever since I've known her. Olga has worked on an impressive variety of astronomical surveys, the VMOS Very Deep Survey, the Cosmos Survey, the Vipers Survey, and the VMOS Ultra Deep Survey, these very clever names, all V related. So that was with VLT and VMOS, which is where, so I met her under the context of Woods, working on galaxy evolution as a function of environment. And she's now taken a turn to the dark side. So she's moved over to simulations, and she's going to talk to us today about protoclusters, synergy between simulations and observations. So please, Olga.
Thank you, Brian. Thank you for the nice introduction and for inviting me here. It's been a pleasure so far. We'll see you in the next days. Today I will present you some thoughts and some results about how it is interesting to explore the synergy between simulations and observations for the case study of protoclusters of galaxies. Taking it from truly the very beginning, my original motivation, then a little bit got lost while doing this analysis, is to study how environment affects galaxy evolution. So just from the basics, we do expect an evolution from disk-like star-forming blue galaxies to elliptical, passive, and so red-colored galaxies. The thing is, there is also an evolution not only in time, but also in some sense in environment, because what we observe in the local universe is the very well-known correlation between the galaxy properties and the local density. So this means that redder galaxy lives on mainly in a higher density environment. Now, as I said, we know this relation in the local universe, but basically in the local universe, we observe the very final stages of this evolution, of this environmentally driven evolution. And so I think that is very interesting to go back in time and try to track the onset of these environmental effects on shaping galaxy transformation. The thing is that environment evolves as well. So we need basically to study the coevolution of galaxies and the formation of structures in the universe. This is a very simple sketch that I took from Rosati 2018. And you can see that if you take a single cluster redshift 0, going back in time, its shape is very, very different. Up to when we arrive to the early stages of cluster formation, where all the galaxies are basically distributed in a kind of more homogeneous way with respect to the very clustered objects in the local universe. Now, at the same time, galaxy evolves as well, galaxy properties as a whole, so galaxy statistics. This is the most famous plot by Maddow and Dickinson that show how the cosmic star formation rate density vary as a function of redshift. We already know that environment, for instance, plays a role in the decrease of this of the cosmic star formation rate density from redshift, let's say, to the local universe. It would be very interesting to know also to understand whether environment plays a role also in the early stages. And in any case, this plot is a very simplified version of what is we think that we know about this cosmic star formation ray density. So you can see that above redshift maybe 1.5 or so, the situation is much more confused. But in any case, what we want to do is to understand how we can link environment basically to this kind of evolution. And so our plan now is to identify structures in formation, such as the protocluster of galaxies. What we should expect if we try to compare galaxy clusters and protoclusters. So galaxy clusters, well, they are objects that have already undergone collapse, so their overdensity is very high, above 200, as you can see. You very well know this magical number, and they, well, on average have a roughly regular shape, and of course there is already intra-cluster medium that is already heated because the potential well has been, it has already had the time to build. For what concerns galaxy properties, we do expect that star formation, as I was saying at the beginning, is mainly quenched in galaxy. And so the quiescent galaxy population is the one that is dominating, especially the cluster cores. On the contrary, for galaxy protoclusters, well, these are objects that are about to undergo collapse in the best cases, or they are still ongoing. And the local overdensity, because of this reason, is very, very low, is between 2 and 20, which is 2 orders of magnitude smaller than the cluster in the local universe. They have a very large spatial dimension because these objects have not collapsed yet, and they have very irregular shapes. For what concerns galaxy properties, on average, what we would expect is a high level of star formation. At the same time, I will come back to this, we might expect already some quenching ongoing. So the two main differences between cluster and protocluster are the mass distribution and the galaxy population. So let's give a look to the mass distribution as seen from a simulation. As I was saying, we do expect a very low density contrast and the fact that the mass is mostly distributed in filaments. In this picture, there is an example of a cluster at redshift 0, and you can see 3 stages of the progenitors of these clusters from redshift 0.6 to 3. And you can see that galaxies going back in time are more and more spread, and their distribution is more uniform, and they can cover basically much larger volume. And ideally, the fact is that while at redshift 0 it is very easy, let's say, to identify a cluster, at higher redshift, if we want to identify a protocluster, ideally we would like to identify this entire structure, so basically all the progenitors that are going to form a cluster at redshift 0. At the same time, simulations can also help us in saying, hey, there is this main progenitor of a cluster that is the main halo that, if you go back in time, is the halo that always contained normally is the biggest halo of the final stage of the cluster formation. But if you go back in time, this so-called main halo that has some kind of definition by construction is not telling you the full story if you go back to redshift 3. So while at redshift 0.6, the main halo is still enough to identify the vast majority of the mass, if you trace it back in time, this is not telling you the full story at all because the mass is much more spread around. For instance, this plot on the left show the fraction of the mass. So you take a cluster at redshift 0, you take its total mass, and you trace back in time with this continuous line, which is the fraction of the total mass at redshift 0 that going back in time was comprised in the main halo. And you can see that this fraction decreases very rapidly down to redshift 2. And for instance, if you look to this plot on the right, at redshift 3, the main halo is basically comprising way less than 10% of the total mass at redshift 0. This is one of the reasons why we truly need to find a different approach to identify protocluster. For what concerns galaxy population, again, from the point of view of simulations, what we do expect is that at the beginning there is an inside-out growth. So basically, the gas inflow at the center of the dark matter halo, well, the potential well is higher, and you have a lot of star formation in the very core of the protoclusters. As the time goes by, you have an extended star formation because matters, all kind of matters, build up towards the core. So you start having a larger volume occupied by star-forming galaxies that are being attracted by the central core. At the same time, you have already some quenching ongoing. And then we get to the final stages where you basically have the final inflow of the structures, and so of all the galaxies within it, and a much stronger quenching. The plot on the bottom show that the cosmic star formation rate density that I was showing you before, it is shown in simulation that the fraction of this star formation rate density in a protocluster is increasing with going back in time. And for instance, already at redshift 3, it is already almost 20% of the total cosmic star formation rate happening in the universe. And it is happening in protoclusters. Now, the things in real life are much more complex. Because at fixed redshift, the protocluster can have a very large variety of shapes and states of evolution, not only for what concern how the dark matter assembly, but also, of course, the embedded galaxy population. So on one side, as I was mentioning before, we expect that the gas cools in the most high dense dark matter halos, and so we have a population of star-forming galaxies. At the same time, this very large gas reservoir plus the higher merger rate of galaxies can trigger supermassive black hole and formation of radio galaxies that have a very strong, on average, negative effect feedback on the galaxy embedded in the protocol in these structures, and so we do also expect a rapidly quenching population. This is just a very a collection of a few examples of protoclusters that have been found recently, let's say, in the literature, and you can see that they have been identified by very different galaxy population, from red galaxy to star-forming galaxies, from Lyman alpha emitters to dust-obscured galaxies, or they have been exactly found around AGN and around radio galaxies, and so forth and so on. So the population is very, it is not homogeneous at all. Moreover, they are also, protoclusters are also very difficult to identify for the reason that we were mentioning before, so the very low density contrast. And so basically, up to very few years ago, what we had was just single and serendipitous detection that basically were covering a vast range of overdensity, redshift shapes, galaxy population. So a very unhomogeneous sample of a protocluster. Fortunately, there have been many attempts recently of systematic searches for protocluster, although the scales on which we should look for them is not totally clear yet. So this is just a list of methods that have been used. They go from just using deep imaging surveys, so the use of dropouts technique or narrowband filters or photometric redshift. Then, of course, also the use of spectroscopic, deep spectroscopic surveys, and then again, the synergy between photometric and spectroscopic redshift. There have been also attempts to reconstruct the distribution, not of the galaxies, but for instance, of the infant ICM in protoclusters, basically just using Lyman alpha tomography of galaxies in the background. So as you can see, the method that would allow us in principle to have an homogeneous definition of galaxy protoclusters the technique are there, and they are being implemented in more and more refined way. So for what concerns instead the galaxy populations, in reality, to make the long story short, what we think is that basically there is a very accelerated evolution of galaxies in protoclusters, and so protoclusters are often associated with a high level of star formation. This is one example derived by a paper by Brian, and as you can see, the average star formation rate in galaxies as a function of the local density is increasing, especially for the highest stellar masses. And you can see that especially in the region where you can find the peaks of a protocluster, you have an average, an increased star formation rate. At the same time, given exactly because we do expect an accelerated evolution, there is a very quick stellar mass assembly, and also the quenching is progressing very, very fast. So basically, the fraction of red galaxies, of passive galaxies, increases very rapidly, already at a redshift about 2.5. And as it is shown, for instance, in this plot where you see the fraction of passive galaxies as a function of density in each of the three panels, and this fraction increases with density even up to redshift 2. So the situation is, well, is quite interesting. Now, where we do kick in this context with our work, well, we started by using the VMOS Ultra Deep Survey, which is a deep spectroscopic survey of about 10,000 galaxies distributed in the field for a total of 1 degree square area. The targets were selected mainly using a preselection in photometric redshift, and two different GRISM, a blue and a red one, were used to cover a very large wavelength range. Of course, the field have been chosen also to have a wealth of ancillary imaging in each of these fields, so to be able to characterize better the galaxy properties. Now, as it happens in life, so woods didn't grow alone, and at a certain moment we realized that it would have been great to merge this SPECSI survey at higher redshift with the ORELS survey, that is a systematic search for structures on a large scale around already known clusters at redshift about 1. The PI is Rory Lubin, sorry, I forgot to mention. And it is how the C3VO survey basically was born. Apart from the original data set of these two surveys, we have been following up many of the structures that we found at higher redshift with very different instruments that are providing us very interesting data that are under analysis in this moment. And this is, well, at least I hope I didn't forget too many persons of C3VO members and friends that have been working, maybe will work in this collaboration. So the method that we apply to search systematically for overdensity peaks at high redshift is the Warren Monte Carlo method. We basically use in synergy spectroscopic and photometric redshift. We work in 2 dimensions in redshift slices. Photometric redshift are used statistically, so basically we do 100 Monte Carlo realization for the PDF of each photometric redshift. So for each 2-dimensional map, we basically have 100 realization of the same map. We average them, and for each redshift slice, we have basically an average 2-dimensional map. And then the final density field for each map is basically simply regridded on a regular grid, and then all these regular grids at different redshift are just piled up to be basically the 3rd dimension, and we identify structures as contiguous volume that comprise overdensity above a given threshold. This is an example of this exercise. This is taken from a paper that instead is related to the ORELS survey, and in this case you have an example of structures at redshift 0.9, but the method is exactly the same. So these are just a few examples of some of the structure that we've been working on recently. The method has been applied to the entire wood sample. These are protostructures in the 3 different fields. You can see that they span a very large redshift range from 2 to almost 5. And just stay tuned for the paper that will describe the method as a whole with the entire catalog of protostructures in wood. Now, let's go back to the main topic of my talk. Now, the synergy between observation and simulations. I think that there can be many, but I want to talk to you about mainly two different issues. That is the synergy with the simulation that can allow a better identification of protostructures and a better characterization of galaxy and structure evolution. Let's start with identification. Basically, in simulations, you know exactly how dark matter is placed, so you know exactly how the dark matter halos are distributed. And the best part is that you also know how galaxy trace these dark matter halos, because for each galaxy, you know its membership to a given structure. We started basically this work with using the Hyperion proto-supercluster as a test case. So this is a very large structure that we identified in the cosmos field at a redshift about 2.4. It has a very large extent in co-moving megaparsecs, about 60 times 60 times 150. And it comprises basically 7 very high density peaks that have total masses between 10 to the 14 to a few 10 to the 14 solar masses. And this is going to be my test case for the next slide. So we also verified that this is a picture of the main of the highest density peaks in Hyperion, and you can see these are all previous literature, so previous findings in the literature of overdensity peaks in the same volume of space that have been carried on using very different tracers, and you can see that we were able with just one survey to span very nicely to cover homogeneously all the previous identification that have been done in a very heterogeneous way. Now, the simulation that I've been using is the Gaia galaxy formation model. It is a semi-analytical model that is run on the Millennium simulation, and it is I list here all the references. It was basically, let's say, the seminal paper was dates back to 2007, and it has been constantly updated. So in this work, I use one of the latest version of this model. In particular, starting from the snapshot of this simulation, I built a dedicated light cone to be sure that, in building the light cone, we didn't miss or disrupt any large-scale structures. And to this final mock catalog, I applied all the same observational biases, as similar as possible, the same observational strategies that were applied to build the Woods survey, so that we are mimicking our data with this light cone, with all the possible biases that can arise. Just to give you an idea, on the left you have Hyperion, and on the right you have, only a fraction of the total volume of the Gaia light cone that I've been investigating. I apply exactly the same method that I applied to identify Hyperion, and this is a volume that is more or less 8 times larger, and I will focus on this volume in the simulation to tell you the rest of the story. I mean, we are undergoing an exploration of a much larger volume in this moment. The thing is, there was indeed in this volume, there was that we first explored, there was indeed a structure that was very similar to Hyperion. You have here the main characteristics and the comparison between Hyperion and this structure that we found in the Gaia light cone. The volumes are basically the same, the mass is very similar, and also the extent is very similar. So from basically tens of co-moving megaparsec. Now, what is interesting in the simulation is that we can also have a very clear glimpse of where galaxies are located in the light cone before applying observational biases, like the fact that we have only a fraction of spectroscopic redshift. We do have fingers of gods, etc. So in this picture, I'm plotting basically all the galaxies in the light cone with an I-band flux of 25, because it was the same flux that cut flux that we applied in the real data. And these are basically all the galaxies. The green ones are those that are in an overdensity that is above the threshold that we use to identify Hyperion, and so to identify this structure. And just pay attention, given the spectroscopic sampling rate in Woods, basically for the reconstruction of the overdensity field, I used only 25% of these galaxies with their original spectroscopic redshift, and the remaining 75% was used as a photometric redshift. What is now even more interesting in simulation is that once you identify your structure at a given redshift, so in this case a 2.4, you can use the merger trees of these galaxies in the simulation and go forward in time and see in which clusters these galaxies will be by redshift 0. And so now these are again the galaxies in this observed at redshift 2.4 in this simulation, but now the different colored sets are represents galaxies that sets of galaxies that will become a different 10 to the 14 clusters by redshift 0. So this picture alone is already telling you that structures like Hyperion is indeed embedding what we can truly call protoclusters. So sets of galaxies that will become clusters by redshift 0. As a bonus, I just wanted to mention also, given that is it's very useful nowadays, that as a bonus, the synergy with the simulation can help us in identify structures in general, not only in data that we already have, but also to plan future surveys, to plan basically observational strategy for spectroscopic redshift surveys, for which it is very important to carefully plan how to use the exposure time to maximize the return in terms of given science cases. This is an example of how many groups you can recover it with at least 2 members if you use a very different spectroscopic sampling rate in any case, in any future survey that you want to adopt as a function of the stellar mass of the galaxies that are embedded in the simulation. So from this plot, you can, for this kind of plots, you can, for instance, decide which is the best compromise between a spectroscopic sampling rate and stellar mass for your future survey. But well, this was just a digression. So let's go back to the synergies with simulation and now move to the galaxy and structure coevolution. Very quickly on galaxy evolution, because this is something that is a work that I just started. So it is very important to give feedback to simulation when we work with our observational data, because we need to refine the prescription for physical processes that are embedded as recipe, let's say, in simulation. At the same time, simulation can give us back us as observers, can give us back an help to interpret our results. Well, why not? These simulations can also help us to, as observer, to have a better insight on how to plan future proposal for follow-up, tackling very specific questions. This is just an example, well, maybe a dirty one, should do better. But in any case, on the left, you have a plot similar to the one that I show you already. The star formation rate is a function over the overdensity in the Woods field. And on the right, in the same light cone that I showed you before, this is exactly how the star formation rate on the same scale as in the left panel, how the star formation rate varies as a function of density. Sorry, sigma here is a proxy for the density in the Gaia light cone that I was just exploring. So you can see that the trends are very similar. Any kind of similarity or difference will be super important to go on with this kind of search and to give us double feedback, two-way feedback to and from simulation. Now, let's go back instead to the evolution of structures. One thing that we can do is to link progenitor and descendant, thanks to the merger trees that are embedded in simulation. And so we can study basically the environmental histories of galaxies. So all the environment that they passed through during their lifetime. So going back to real data, my point in the exercise was to see whether Hyperion was in some sense linkable to this supercluster that was analyzed in the ORELS survey at redshift 0.9. This is the supercluster SC1604, and you can see it is basically a collection of many different structures that are very close in a Ra index. I think these are kind of 25 by 25 moving megaparsec or something like this. Now, I was just playing a little bit with the simulation, and I wanted to see how the halos at the redshift of Hyperion would evolve at the redshift of SC1604. So I just took some halos in the Millennium simulation, irrespectively of their position, and at the redshift of Hyperion, and on average, their evolution at the redshift of 1604 is this one. And now what happens if we overplot the data that we have in our hands, so the total masses of the peaks in Hyperion and of the clusters that are embedded in 1604, you can see that the correlation is very good. So on a very general extent, we might say, hey, look, it is not that improbable that 1604 is a descendant of Hyperion, but we did things slightly little in more details. So let's go back to the structure that I was showing you before, the one that we found in the simulation, and let's focus on the highest density peaks, those that have an overdensity above a 5 sigma threshold, that are basically the reddest colors in this picture. And if you focus on them and you go back and collect back in time the halos that are descendant of these 5 sigma peaks, this is how they are distributed in space at redshift 0.9 on the top right and redshift 0. So first of all, you can see that there is, well, dark matter is building up, so you go from a dozen of very massive structure at redshift 0.9 to basically much lesser and more massive structure down to redshift 0. I'm plotting here just the most massive one. There are plenty of truly small halos at redshift 0.9 that are also descendant of this large structure. And by small, I mean masses less than 10 to the 13. Now, the thing is, if we go back to the shape of 1604, well, this structure is not truly the possible descendant of one single 1604, but probably two, given the extension in co-moving megaparsec, and also given the fact that by redshift 0, these two substructures will be truly separated in space. And so this was just a test case that we just finished exploring. And now this is the previous plot, and now in purple you see all the masses.
Okay, so can I
yes.
ask a question? So the peaks at redshift 2.5 are how distant from one another in co-moving megaparsec?
Sorry, this is more or less this is 150 megaparsec or this.
And it's the same at redshift 0.9, so the separation between the two agglomerations.
The separation, sorry, yes. I don't know whether also the people online can see the arrow. The separation between these two is basically the separation between these two blobs.
Okay, so basically there's no interaction between those.
No, apparently no.
Okay, interesting.
At the end there is nothing massive between these two groups of peaks. As exactly because I was saying, the 1604 has a kind of a size of a few tens of megaparsec, 30 or something, co-moving. These are truly too distant to be considered just one single 1604 analog. So this is the plot that I was showing before, but now in purple I'm adding all the masses of at the redshift of Hyperion, I'm plotting the massive of the 5 sigma peaks that I found in that structure, and at lower redshift, I'm plotting the corresponding descendant of the halos in the simulation. So now the thing is, of course, as I said, there are many similar structures in the entire light cone. So what we would like to do now is to analyze all these other structures, and apart from this single example, we want to derive some kind of general statistical behavior, if any, because this is not even given for granted. So just to go to my summary, I would like you to take home some messages, and especially that protocluster can exist in a large variety of shapes and stages of evolution, and so can embed very different galaxy populations. And we truly need a model of galaxy formation and evolution to understand our observational findings in terms of whether what we find is truly potentially a protocluster, or maybe just a sparse group, and to also to derive important pieces of information on galaxy evolution as a function of environment. So it was very, very, very interesting to play with Hyperion. That is a really interesting science case. But the idea here is that we need to generalize the analysis to a larger sample of such protoclusters. And of course, the further step is to move from the analysis of dark matter structures to the analysis of the galaxy populations that are embedded. The perspective for protocluster studies are great, I think, in terms of observations, because we will have soon many cool instruments that will be ideal to study to identify and study such structures. At the same time, what we would need is simulations that can match the very high performances of these data sets that are coming. This is not obvious given the usual trade-off between resolution and volumes covered in simulations. But I think that we truly need to engage both the observer and simulators community in a two-way continuous feedback. And I thank you for your attention.
Thank you, Olga, for the wonderful talk.
Thank you.
It seems as if we have plenty of time for questions, either for the few in the room or anybody over Zoom that is interested in talking protoclusters or anything that Olga talked about. Yes, Roberta.
At the beginning, you showed a plot where you had the cosmic fraction of star formation as a function of redshift, that you show the protoclusters and the protocluster cores.
Yeah.
I don't think I fully understood how that plot was behaving. The part that passed me most is that it seems like this one. So at low redshift, basically at redshift 0, the cores are contributing. The protocluster contribution disappears. So it seems like.
Yeah. So I didn't go in explaining in full details this plot. So yeah, no, your question is correct. So basically, the idea is that in protoclusters you can define the total their total volume, basically, that is this blue circle here and corresponds to this blue line. At the same time, there is already a core in the middle that is building up. As well, you can also see with the 5 sigma density peaks that we found with these larger structures. Basically, the vast majority of the star formation is given by all the galaxies in the protocluster, not only in the core. And basically, as the time goes by, the core, I mean, all galaxies didn't fall into the core. So basically, the core and the protocluster at the end correspond. And especially at the end, the protocluster is a cluster, is no more a protocluster. But this was just a way to say down to redshift 0.
Yeah, no, we're not talking about outskirts.
No. Sorry, it's already, I mean, it's a truly protocluster. Then there is a further step that is defining the core. Okay. But it's not the surrounding. It's already all the galaxies that will end up in being in the cluster by redshift 0.
Yeah, I think their operational definition is it's R2. The core is R200 for the most massive halo, something like that, right? But they basically define the cluster at redshift 0 as that. So R200 of the most massive halo that ultimately the cluster becomes. And so then they, by definition, they have to conform at redshift 0.
Okay.
Other questions in the room or online? While people are thinking, I could maybe ask a question. So I saw that there's the kind of concordance between the semi-analytic model looking at the average star formation rate of galaxies as a function of density with the observational work. That's very ambitious. Like, so this is, redshift 2 to 5. I wonder, do you see that same kind of wonderful concordance in maybe lower redshift, more established relations, like the stellar mass function as a function of environment at redshift 1, where the environmental effects, really can impose themselves? Because this has been a traditional failing of semi-analytic models, at least for the time that I've been looking at them.
No, it is still a failing, because at the lower redshift, if you try to make this kind of study, the stellar mass function or color density relation, whatever, in simulation and in observation, it is still different. What happened at low redshift? What happens mostly of the cases is that there are too many quenched satellite galaxies, because for some reason in simulations, they are, in many cases, well, they are working on it as far as I know, they are too aggressive in shutting down the star formation when a galaxy enters a bigger halo. So when it is accreted, and so it is no more the central galaxy of its own halo, but becomes a satellite of a bigger one. And in that case, this is a semi-analytical approach. So you have just to give prescription, and prescription can just say, okay, the galaxy at the exact time that it becomes satellites, the star formation, the infalling gas is totally stopped, and you don't know everything, and the star formation is also suppressed, like on the spot.
But that's clearly a function of redshift, right? So, in this case, the high intensity environments, we don't see that kind of overquenching. So, yeah, some switch is turned on at, I don't know, when there's a hot ICM or something like that, apparently. Yeah,
these are all things that I think that, for instance, putting together Orels and Woods or many other surveys in the redshift bins in between, if we are able to trace the same, to be sure that we are tracing the same kind of structures and galaxy population at all redshift in observation, I think it would be super cool.
Ambitious.
Yeah, a bit. The other thing is that there are too many. No, it's not only that the satellites are too red, but they are too many, especially the small one. In reality, they should disrupt. A good fraction of them should disrupt, being totally absorbed and cannibalized by other galaxies, etc. While they don't in simulation, and so they are also too many.
And that's a resolution problem.
Sorry?
That's a resolution problem.
Yeah, that's also a resolution problem.
Any other questions in the room? Anybody? Emma?
Emma.
I have two questions, and both showed how much I don't know about the field. The first one is, what is going to change in your analysis when the Millennium TNG will come out? So you have the entire volume, but with like physics and everything, like put it together. But that would be like, how much the Millennium, I think there is now no test on the protocluster in the Millennium TNG, or that I'm not aware. Probably there are, but I don't know sure. But is there anything that would be, you expect to be fundamentally different in moving from a full cosmological way, or you're more educated, like adding analytical model on the Millennium solution?
Yeah, that will be a revolutionary change, because you will have a much more controlled evolution of the gas properties in galaxies, which is one of the things that we are also aiming to try to observe in our data. And also you will have, for instance, a control of, you never know, the nascent ICM within the structures, which is also cool, if possible to be seen. One of the methods that I was showing you at the beginning for this search for homogeneous search for protocluster is indeed to use tomography or Lyman alpha tomography, so to observe the Lyman alpha at the redshift of your structure, absorbed in the spectra of the background galaxies, which would be, I mean, if you have all the particles of the gas in the hydrodynamical simulation, these are things that you can also study in more detail.
But you have a fairly coarse resolution for the TNG. So it's like your similar analytical model wins in some side that you.
Yeah, that's the reason why we are still waiting for huge volume, super high resolution hydrodynamical simulation.
Yeah.
That will be a game changer. Yeah, no, the compromise between the resolution and the volume is one of the, is the issue here in this kind of studies.
And the second question is, you say that is a protocluster is something that will end up in a cluster ratio 0. And what's a cluster ratio 0? Like is a virialized structure or is not virialized structure? Like Virgo. Is that a
Thanks.
We'll talk about
No, yeah, everything in the simulation is very simplified. So what is defined as a cluster is a bound structure. So they just use in this case, for this kind of simulations, for the dark matter simulations only, they use a friend-of-friend algorithm to find how many particles of dark matter are bounded. And basically, once the overdensity is high enough, that will give you a bound structures. And so basically all the, let's say, all the things, all the objects that in the simulation are called main halos by ratio 0, they are basically virialized structures. Then you can have things that do not have at all an homogeneous shape. There might be two very close by, and then you never know what is going to happen in the future. But yes, the situation in the, although the shape is probably preserved, so very merging cluster do exist in the simulation, the definition that we're using is it's very helpful in sense, because it is kind of simplified, because you know where bound the structures are.
So potentially, if you relax your definition of a bounded system at low ratio 0, you can have more Hyperion-like structures, or
it's a good
I have
question.
absolutely no.
No. It's a good question. At the same time, for instance, if you look for any sample of superclusters at ratio 0, you have plenty of different shapes. You have superclusters that are just 3 clusters very close by in a very small volume. You have chains of clusters that can reach 100 megaparsec of length, or so. Also in real data, the situation is very, let's say, changing. I think we would need first we would need a common definition for supercluster ratio 0 before trying to apply to see whether in what we have in simulation is if we relax. We should agree on some kind of definition. Otherwise, we could literally find everything.
In defense of simulations, from an observational perspective, the definition of a cluster, of a group, of a supercluster is somewhat ill-defined. And so applying common, as best as you're able, applying common definitions, then looking for a one-to-one correspondence is important. But also for 1604, what we've seen is our imaging wasn't large enough to pick up the entire structure. So there's people in a group in Japan that's following up on 1604 with HSC and MORCS, and seeing that actually 1604 is potentially multiple superclusters. And so we have a limitation from our data, even though we have a 1 degree field of view. Still, there's extended structure beyond that, and that you have the virtue of the full field in the simulation.
Yeah,
but we don't have that in observations.
That's good.
Any last questions over Zoom? Otherwise, I'll just remind everybody that we have another talk on Thursday at 11 o'clock, same building, new Zoom link, I guess. So this is a CSO TMT. And with that, let's give Olga another round of applause.
Thank you.